Good day, everyone. Today I'll be presenting our first laboratory activity titled Plotting Analog Signals. The main objectives of this experiment are to understand how to generate and visualize analog signals using Python, to apply NumPy in creating time domain samples of signals, and to use Matplotlib for plotting sine, cosine, and combined waveforms. By doing this, we can also analyze signal characteristics such as amplitude, frequency, and phase. For the materials, we only need a computer with Python installed and two essential libraries, NumPy and Matplotlib. If these aren't yet available, we can easily install them using the pip commands pip install numpy matplotlib. Now let's move on to the procedure. First, we import the required libraries. Next, we create a time base using numpy's arrange function. This defines our time vector from 0 to 1 second with a small step of 0.001 seconds to represent a continuous signal. After that, we generate two basic analog signals. A sine wave with a frequency of 5 Hz and a cosine wave with a frequency of 10 Hz. Here's the code snippet for that. We then plot the signals using Matplotlib. The first subplot displays the sine wave. The second shows the cosine wave. And the third presents their combined signal, a superposition of both. Finally, we use plt.show to display all three plots. In the sample output, the sine wave shows smooth oscillations at 5 Hz. The cosine wave at 10 Hz. And the combined signal forms a more complex waveform due to their addition. Now for the guide questions. What happens if the sine wave frequency is doubled? When the frequency is doubled, the wave oscillates twice as fast, producing more cycles within the same time interval. This makes the waveform appear compressed horizontally. Question number 2. How does the phase difference between sine and cosine waves affect their combined signal? Since sine and cosine waves are 90 degrees or pi halves radians out of phase, their peaks and zero crossings don't align. This phase shift creates a more complex waveform when they are added together. Question number 3. What happens when we change the sampling interval? Increasing the interval, like from 0.001 to 0.01, reduces the number of samples, making the signal appear jagged or even distorted due to aliasing. On the other hand, decreasing it to 0.0001 makes the signal smoother and more accurate. but it also requires more computation and memory. Lastly, how do amplitude and frequency affect the signal shape? Amplitude controls the height of the wave. Higher amplitude means taller peaks and deeper troughs, while frequency determines how many cycles fit in 1 second. A higher frequency produces a denser or more compressed waveform. To conclude, this laboratory activity helped us better understand how to model and visualize analog signals using Python. It also demonstrated how small changes in frequency, phase, or sampling rate can significantly alter the appearance and behavior of waveforms.